All right, everyone. We are going to be talking about phase separations. The homework that you will receive over the weekend, so hopefully everyone has access to Canvas mail. That's how I'll be distributing everything. I'll just post the PDF file of the homework. And also what I'll be doing throughout the semester, if I don't have it already, if you go into the files under resources, I have different data tables, Anton's equation, heat capacity. It may be from the Sandler book, it may be one that I think is just particularly useful. I also have an equation sheet that I've made personally that's sort of in lieu of this important table here. That's the one that you'll get on all exams and quizzes. So if you go and look and you find an equation sheet, I think it's very, very useful. I spent years actually refining that sheet. Far more years than I'd care to admit. But it basically has all of thermodynamics and introduction to statistical mechanics on a single sheet. I should print it out and bring it in next week so everyone has a copy of it. So if you go online to Canvas, it may be under exam resources, somewhere in there, go through it. There's a bunch of different data tables. So if I ask you to calculate the change in heat capacity or something like that, and you don't know which data table to go to, check there. There'll probably be one, or you can use the Sandler book. If you use different tables for things like heat capacity, you might get slightly different numbers. I'm not one to ever generally nitpick on the exact details. So if it's close enough, it looks like you've done the work well, you know, all of these calculations are in many ways just limited based on the accuracy of the experimental data. So if you're using a slightly different data table, it's a slightly different fit, you'll get a slightly different number. I'm not going to pull my hair out loosely over it. All right, so with the chatter that was going on before class, today we're going to talk about equilibrium. Now the objective here is calculating state changes of a single-phase, single-component system is relatively straightforward. We have expressions for changes in internal energy, changes in enthalpy, changes in entropy. So by applying the first and second law, right, so just as a recap, so forget about the equilibrium criteria for a minute. So we have expressions for changes in enthalpy, changes in internal energy, and changes in entropy, plus entropy balances and energy balances. We combine these concepts together, right? These were derived from the combined first and second law. These are just bookkeeping, noting that energy is conserved and extensive. Entropy is extensive, right? So we're just keeping track, we're just being energy and entropy accountants. These are the combined first and second laws saying how fluids should behave. And basically what this allows us to do is to balance processes, BALANCE, and calculate whatever temperature, pressure, density conditions would make the best process. Okay. Now, in thermodynamics, the power for chemical engineers is much more than just this here. And I'll be the first to admit that chemical engineers, you know, we're not the end-all, be-all of thermodynamics. When it comes to designing a boiler, a power plant, a heat exchanger, honestly, I would say just give that to a mechanical engineer. They do a really good job at those types of calculations. Right? They do a much more extensive job at understanding the fundamentals of heat transfer than chemical engineers do. However, the one area that only chemical engineers do, chemists maybe dabble a very, very small amount, but chemical engineers almost exclusively handle phase equilibrium. And so what we're going to be talking about now are what are the differences between phases and what are the relationships between phase A and phase B. Now this could be two liquid phases. It could be a vapor phase and a liquid phase. It could be a solid and a liquid. It could be a vapor and a solid. We're going to focus now on single component, which is going to be relatively straightforward. We can cover it today. But then when we go to multi-component, then things get a lot more complicated. So what we're going to do is, again, we're going to start off with one of these arbitrarily defined boxes that allow our derivations to be a little bit easier. Let's see if this marker is any good. I'm going to partition it. On one side, I'm going to call it phase 1. The other side, I'm going to call it phase 2. This is going to be isolated. So that means there's no heat going in and out of the system. That's adiabatic. I don't think we've used that term yet necessarily, have we? The change in volume of the system is going to be equal to 0. So if no heat can go in and out of the system, and the system cannot expand or contract, that means no energy can go in and out of the system. If we also say that dN is equal to 0, right, the change in number of moles, or change in number of particles in the system is equal to 0, that means it's impermeable. So what we're saying here is that if we put these together, that essentially means that the change in internal energy of the system is equal to 0. This is what we would call an NVE system. That's the ensemble that we're working in. The number of particles is constant, the volume is constant, and the energy is constant. But what can happen is in between phase 1 and 2, we can have an exchange of absolutely everything. We can have an exchange of energy, volume, and particles, and entropy. So each side here, the number of particles in phase 1, the internal energy of phase 1, the volume of phase 1, and the entropy. And likewise, we have exactly the same thing here for phase 2 or chamber 2. Right, so we can have an exchange, right? The boundary of where this lies can move, be like the number of particles changing, the internal energy, everything. At equilibrium, nothing is changing. Absolutely nothing. Now, the reason why we're starting off with this derivation here is you'll notice that I'm only working in the fundamental units of thermodynamics. I'm not going to be introducing any other concepts like Gibbs or Helmholtz or enthalpy or anything like that. Right, these three here are the primary intensive units of the universe, and then mass, of course, right? We're conserving mass as well. So what this means is that at equilibrium, ds is equal to 0. The change in entropy is equal to 0. We know that the second law states that the change in entropy has to be greater than or equal to 0. And additionally, due to the stability of the universe, this has to be negative. So if we put these two concepts together, and I am to look at a plot of the entropy of the system as a function of any single one of these variables here, right? But let's just say, we'll just call it some coordinate x. Regardless of how the system should look like initially, we know that the entropy will eventually increase and level off here. And this is going to be our equilibrium. What if it were the opposite? If we had the opposite curvature of entropy, we could still satisfy an equilibrium criteria here, where the change of entropy with respect to time or any other coordinate would be equal to 0. But here's the problem. If I were to have any sort of a fluctuation, anything that's insignificant, let's say I had one particle jump from this side over to that side, or the volume of the boundary moved a little bit this way, what would happen to the entropy of the system? So if I started off right here and I had any insignificant change of any property in any direction of the system, what must happen to the entropy? It must increase, right? So this is an unstable system. So if I go this way, the entropy increases. If I go this way, the entropy increases. So this is unstable. Yes?
The first graph, you said the point as the equilibrium because it's the maximum point?
Correct.
Because it's at the end?
It would be the maximum. So for example, the system really can behave like this. So thermodynamics is an average. So StatMech introduces the concept of particles and the statistical motion of the particles. So in the case of here, this is the equilibrium,
Okay.
what I would call the bucket value, right? So if you're trying to measure the flow rate of a stream, right, there's going to be velocity distribution, there might be fluctuations, but the bucket value is, okay, what's the flow rate every minute? Put a bucket underneath the stream, measure it for a minute, and that's the value you get. So this is the macroscopic property. So in contrast, let's say we do have a statistical fluctuation, because we do. That's the origins of Brownian motion. It's the origins of diffusion. It's all the kinetic properties of the universe that we're accustomed to, right? In that case, we would have a little bit of a statistical fluctuation this way, a little bit of a statistical fluctuation that way, and look, your entropy is lower, which means that the system will recover and go back to the steady equilibrium. This is stable. So who has experienced superheating of water? You're boiling a pot of water and you put the pasta in and it boils up violently all of a sudden, okay? Or you've seen like the trick where you freeze a beer bottle and then you tap it and then it crystallizes and forms right away. Right, so what's happening here is that you're actually exceeding the equilibrium, but the fluid is still stable. Now you can heat something up and there's a limit to how much you can superheat it before it actually just spontaneously starts boiling. That is governed by when the fluid becomes unstable. So entropy is the driving force for all phase changes. And we'll talk about that more so when we, maybe today, but probably early next week, we'll talk about that. So superheating and subcooling is permitted, but once you reach a certain point, the fluid will become unstable. And once the fluid becomes unstable, what that means is that any sort of rotation, translation, movement, vibration, any sort of movement that happens with that fluid will cause the entropy to increase, and sort of you can think of it like it's always going to happen. But on a stable fluid, right, there is a barrier of entropy. So entropy basically forces everything to go to the equilibrium state. And so the phase change, we'll talk about a little bit, actually you have to steal a little bit of entropy to overcome a barrier. Yeah.
We don't have to go down this rabbit hole if you don't want, but so with your beer bottle example, when you tap it and it comes out of its unstable equilibrium and starts to freeze, when it's freezing, isn't the entropy decreasing? Like it's becoming more crystalline?
Yes.
Or am I not thinking of that right?
No, you are thinking about that right, but in that case, that would be an NVT system, in which case equilibrium is at dA, so A is equal to a minimum. So it's not strictly entropy. In this case, this is an NVE system. In this case, S is equal to a max, and we'll talk about this just very briefly. In an NVT system at constant temperature, the equilibrium is dictated by the minimum Helmholtz. So that's U minus TS. So what ends up happening is going to a crystalline state. The amount of energy that you save overcomes the loss of entropy.
Oh, okay.
And in the case of an NPT system, the Gibbs is equal to a minimum, in which case is Helmholtz minus, enthalpy minus TS. So in this particular system here, entropy being maximized is the criteria for equilibrium. But in isothermal systems, you have to consider internal energy and enthalpy.
Okay.
Yeah, so these are constant energy systems, right? So the amount of energy that the system starts off with is based on how many particles, what's their internal energy, and so on. But no energy can go in or out of the system anymore. Okay, but good question. All right, so that's the criteria. Now let's look at what that means in practice. So how do we actually maximize the entropy? So what we're going to do is we're going to look at the total entropy of the combined system, which is going to be equal to 0 at equilibrium, which is going to be the change in entropy of phase 1 or side 1 plus the change in entropy of phase 2. So these two processes have to be balanced out. Then we know we're at equilibrium when we can satisfy this expression right here. So what we're going to do, we're going to expand entropy with respect to all of the other variables in the system. With respect to internal energy, We'll do this example for side 1 with respect to the number of particles with respect to the volume. And this is going to be symmetric, of course, the exact same expression, but just change the numeral 1 to a numeral 2. So this is going to be exactly what we did for all of our other derivations. Change in entropy of side 1 with respect to changes in internal energy of side 1 at constant volume of side 1 at constant n of side 1. And that will be u1 plus. All right. So a couple of simplifications that we can make. This expression here, this is really just the definition of temperature. So this here is a thermodynamic identity. This is just the reciprocal of the temperature of chamber 1. Similarly, we can show that for an open system, this would be equal to the Gibbs free energy of side 1 over 2. And I think this one should be on your sheet as well for the thermodynamic identities. It might be on the bottom of the page. We haven't talked too much about the chemical potential, but this is effectively what they call the chemical potential. For this last one here, we'll do it as an example. Let's expand this with the triple product rule. So we'll play around a little bit more with this one. So here, we'll start off ds dv at constant u. And then for the triple product rule, you kind of just go in a rotating manner here. So this would be change in internal energy with respect to entropy at constant volume, and then the change in volume with respect to internal energy at constant entropy is equal to -1. So all I did is I moved what's constant to the numerator, and that to the denominator, and that to the being held constant, and do that twice. This is equal to temperature. This is what we're trying to rearrange for. This one is -1 over pressure. So then we'll find that this term here is equal to P over T. So in this case, it would actually be P1 over T1.
Is there a zero?
Well, yeah, I'll say check. That's the one we're trying to solve for, to make it not confusing. Okay, so let me try and partition this off. We're looking at when does the total change, or the rate of change in entropy equal to 0? We'll substitute these expressions in here. So this is going to be 1 over the temperature that's right. To minus here, minus. We're almost there. What we're going to do is perform an energy balance, an entropy balance, and in this case, I guess, a volume balance because the volume of the whole system is conserved. The total change of the number of particles in the system is also going to be equal to 0 because that's what we defined. We said this is an impermeable system. So that means that the rate of change of the number of particles in phase 1 plus the rate of change of the number of particles in phase 2 is equal to 0. Our conclusion then is that any particles lost from phase 1 are gained in phase 2 and vice versa. And the same thing applies for energy, volume, and entropy. So du of 1 2. All right, almost there. One last step and we are good to go. So if we substitute it all together, so all I did was combine these two terms here and substituted out the change of 2 for the change of 1, so that's why the sign changes for all of those terms. So the only way that we can unambiguously have everything always equal to 0 is that this first term has to equal 0, the middle term has to equal 0, and the final term has to equal 0. And that establishes 3 criteria for phase equilibrium. Number 1 is thermal equilibrium.
Why do they need to be equal to 0?
Because in order for this system to be at equilibrium, the rate of change in entropy has to be equal 0, meaning that we are at the maximum entropy condition.
So all 3 or just 1? Oh, no. That's
So
fine.
all of these. So the only way that this equation always goes to 0 is that if each is.
Yeah.
Now you could imagine maybe some scenario where it like counteracts and balances, but the only unbiased way that we can always get equilibrium is if the temperature of phase 1 is equal to the temperature of phase 2. We have mechanical equilibrium. In which the pressure of phase 1 is equal to the pressure of phase 2, right? That volume boundary is at a position of stasis. And the last one is chemical equilibrium. In which the Gibbs of phase 1 is equal to the Gibbs of phase 2. And this is how we know that we have a system in equilibrium. Let's recap. Let's remind ourselves, how did we get here? What we've done is we created an isolated system. Now that isolated system, the variables being held constant are the number of particles, the volume, and the energy of the system. The only additional thing that we have invoked is 2 concepts. Number 1, at equilibrium, the system's at equilibrium. Basically, by definition, nothing's changing. It's a static, stasis, equilibrium, constant system, invariant with respect to time, which means that no variables can be changing. The only additional thing that we've thrown in here is that entropy always increases. And that entropy, by stability criteria of the universe, has to be concave. right? So we're really only invoking the second law of thermodynamics and designing our system. So the consequence here then is that when we expand our criteria for equilibrium, we have to expand it with respect to all variables in the universe. The Gibbs phase rule says that we only need to expand it with respect to two intensive variables. In this case, it's an extensive system or an open system, so we have to include the number of particles. And the rest of it here is just the mathematical manipulation that we talked about by general, number one, definitions of functions, right? We're defining temperature, we're defining pressure, right? And the reason why we have defined them is because, number one, they're easy to measure, and number two, they govern the criteria of equilibrium. So this is unbiased. I haven't talked about phases or anything like that. This is all very fundamental thermodynamics with no assumptions. There's absolutely no assumptions that have been made in this derivation other than defining temperature and defining pressure and defining Gibbs. Right? These are just made up functions that happen to be convenient. So going back to the question we had earlier about Gibbs and Helmholtz and equilibrium criteria that we're more used to, right? NVE systems are not ones that we're necessarily going to encounter on a regular basis. Constant temperature is more so what we're going to be encountering. So I'll show you for a constant PT system how we arrive that the Gibbs free energy is minimized in a constant PT system. So let's look at an energy balance. In this case, we'll have it be, I have it closed. Right? No work, simplify our expressions, no mass flowing in or out, so the change in internal energy is just how much enters or leaves in the form of heat, how much energy enters or leaves when you compress or expand the system. Our entropy balance, in this case we're going to say S gen is equal to 0 just to make our lives a little bit easier. Just kind of rearranging things a little bit to make the derivation look a little bit prettier. In this case, we know that t is constant, so we can move it in and around to the differential with any concern. We don't have to take any product rules or anything like that because we know it's going to cancel out. Okay, so then we substitute the first, second law together. So this is d t s t minus d t. If I move everything over to one side of the equation, it's going to be u plus p v minus t s. And if this seems very convenient, that's because it is very convenient. Because we have defined the Gibbs free energy in order to satisfy this criteria. Now, I don't recall exactly if we talk about it, but I'll briefly mention that due to stability, Gibbs free energy always has to be convex. But you kind of make hand-wavy sense, right? Because there's a reciprocal relationship kind of between, as entropy gets bigger, Gibbs gets smaller, so it kind of makes sense that this is the case. So that's how we know that the Gibbs is a minimum and not a maximum at equilibrium. It's a consequence of stability. Likewise, we could do basically a similar derivation in this case here. If we say it's a constant volume system, that goes away, then that goes away, and then at a constant volume system, the Helmholtz. So in this case, A equals min at equilibrium in a NVT system. Again, if that seems convenient, it's because it is. We have defined the Helmholtz energy to satisfy that criteria. And I always like to acknowledge, the contrived nature of everything that we're talking about. And it's contrived because this is the best system that we've come up with to keep track of thermodynamics. You could conceive of another way where you couldn't violate the first and second laws, but that maybe is more complicated. This is the way we've done it. All right, one more thing really quickly before we get to talk about how we actually can use this information sort of for practical good. We'll rely on this same system here. And I'm not going to go through the math because, number one, I haven't actually personally gone through it to the full extent. I trust the Sandler book, and I will show you why I haven't gone through it, because it is heinous. Let's apply the criteria. That entropy has to be convex for this system, which means that we have to take the total differential which is the total differential of this system here. So very briefly, this expression here, the change in entropy of side 1, I think it has since been erased, is equal to So I have 1, 2, 3 expressions, double it for this one here, 4, 5, 6 expressions. Then I have to take the total differential of this one, and this one. So if I take the total differential this is going to have how many terms? I'm going to have some du1 plus some, du1 dv1 plus du1 dn1, which means that I'm going to have 6 times 3, 18 different expressions. And then I have to somehow squeeze them all together and come up with some sort of a coherent, reasonable system. Right, so I have to take the total differential of a total differential for a system that has 3 independent variables. I have a personal life. I have chosen not to do this derivation. But I trust that our thermodynamic leaders of past have successfully applied it. Oh, sorry, no. It gets worse than that. After I have to do that, then I have to apply it's not an equal, right? I determine what criteria will satisfy that this is always going to be, less than 0. Sorry, my bad. That this is always going to be less than 0. An inequality I have to then determine under what criteria the inequality is going to be satisfied. So I'm sorry that I can't walk you through the beautiful elegant derivation. I don't think it's worthwhile. So needless to say, after a lot of math, we come up with some nice conclusions. One, the heat capacity always has to be greater than 0, and recall that heat capacity is defined as the change in internal energy with respect to temperature at constant volume. And you can kind of see how heat capacity would be substituted in here, right? Probably in an expression like here, right? So what this tells us is that if we ever want to increase the temperature of the system, we always have to give it energy. We can never spontaneously heat up the system without giving it energy. That makes total sense to me. But as it turns out, that is not an intuitive conclusion unless you account for the stability criteria of the universe. Entropy must be convex. And also, this is the one that we'll talk a lot about. Pressure and volume must have a reciprocal relationship, meaning that as pressure increases, the volume must always decrease. And this is going to be our pathway into actually calculating phase equilibrium. So, very quickly, let's look at the ideal gas law. Now, this is a trick that I like to do because I'm not particularly good at math. When I see a function like this, I have to go back to my Calculus 1 days and I have to make sure that I get everything that's not pressure to the other side of the equation. So I always rewrite my expressions like so. And then I can take a derivative. So in this case here, the change in pressure with respect to volume while holding temperature constant is equal to what?
Negative RT over V squared.
Yes. Does this equation of state violate the second law of thermodynamics? No. Under what criteria would this equation violate the second law of thermodynamics?
0 temperature.
Not 0 temperature. Well, actually, is this less than 0 or less than or equal to 0? Anyway, well, the third law of thermodynamics stipulates that you can never reach absolute 0. And you can actually derive that by looking at more or less what we've done here. But basically, if we assume that temperature can never equal 0, right, and that density can never be negative, then this is always stable under all circumstances. Always stable. Success. We have not violated the second law of thermodynamics. So what this looks like, again, borrowing from, let's say, I don't know, algebra 2 now, what does this function look like if I were to plot it? Pressure versus volume at a constant temperature. What does this function look like? No, sorry, this one look like.
So it's a diverge close to.
Yeah, it's a radical function, right? Yeah. Looks like this. So any stable fluid must look like this, and it must have this curvature here, right? The slope at any point corresponds to the partial derivative of pressure with respect to density, and it always has to be negative. And if it isn't negative, then we've got a big problem. So let's talk about some other equations of state then. So ideal gas law, great. But what happens in the ideal gas law? As I take a really low pressure, really high specific volume system, and I keep pressurizing it, and I keep pressurizing it, and I keep pressurizing it, do I ever have a discontinuity in the system? What happens if I keep pressurizing an ideal gas.
Yeah.
It's just a fluid that just keeps on getting squeezed closer and closer and closer and closer together, right? So it's effectively like we're looking at a supercritical fluid, right? There is no phase transition. There is no point when you pressurize an ideal gas that anything happens. So let's look at a different equation state. So if you guys can recall, what's the next most complicated equation of state that you may have looked at in undergraduate? That's actually a big step up. There's one minor one. It's ironic because van der Waals came before this one.
Oh, is this the one with the power?
The virial equation of state. So look at the virial equation of state. Oftentimes, so virial equation of state was actually derived probably in the late 1800s. Van der Waals, oh boy, I think it was early 1800s that the van der Waals was derived. I have to double check my history lecture. This one's often written so we could rearrange this here to a more conventional form, ZRT over B plus RT B over B squared. In this case, Z, this is just another useful, convenient defined function. Oops. We just say it's equal to 1 if it's an ideal gas. So, we could also take the second derivative here, but I prefer to do something a little bit different. We can rearrange this expression to make it look a little bit different. Right, this is a similar mathematical substitution. We're just rearranging it to make it look like a polynomial. What order polynomial is this? Second order, yeah, I'll call it quadratic. So in the case of the virial equation of state, if I were to plot out the virial equation of state, it will look like this. A parabola, right? This is just it'll have a positive curvature here, right? Because you can never have a negative pressure, you can never have a negative temperature, you can never have a negative density. So the second derivative of this is always going to be positive, so it has to be smiling up. But there's a problem. Everything on this side is stable, everything on this side is unstable. So this is just kind of a mathematical complication. You always want to go for this root on that side, right? So if you try and solve this quadratic equation, right, you're going to get two answers. One of them is going to be a fantasful, unstable fluid. The other one's going to be the real fluid that's actually stable. Right, so let's say we start off at some ideal gas state over here at really low pressures, really high specific volumes. It has exactly the same problem that the ideal gas law has. These equations of state are so bad that they don't even predict that liquids and solids exist. Now, we will bring in the van der Waals equation of state. So, if we can kind of think as the ideal gas law as, I guess, radical, but let's just say it's a first order polynomial. Second order polynomial. What do we think the van der Waals equation of state is going to turn out to be? It's going to be cubic, or third order. So if we take a look at the van der Waals equation of state, this expression can be rewritten, and we'll go over this a bit more, but just to highlight it here. And this is where we get the term cubic equation of state. So in addition to the van der Waals equation of state, the Peng-Robinson is a cubic equation of state, the SRK is a cubic equation of state. What makes them cubic is they can all be rewritten this way here. This is another nice convenience about how we formulated thermodynamics. Because if you write code that can calculate phase equilibrium using a cubic equation of state, using this generalized notation of A, B, C, and D, if you want to change the equation of state that you're using, just change A, B, C, and D. And your equation, so your code works perfectly fine. So now what a cubic equation of state will look like, let me rewrite this so we can really talk about the details. Because this is where the fun, I think, really starts. All right, so let's draw this very large. The cubic equation of state, if the temperature is greater than the critical point, then a fluid kind of should behave a little bit ideal gassy. In which case, you are going to have just a radical type function. In this case here, these are what we call isotherms, meaning constant temperature lines. So we're only changing P and V with respect to constant temperature because we are trying to assess the stability criteria governed by the second law, which we skipped over the math of, having to always be negative, right? So there has to always be a reciprocal relationship between temperature and pressure. Volume goes down, pressure goes up, sorry, P, V. Now what ends up happening, however, is that as you approach the critical point of the fluid, it'll start to behave a little bit differently. And eventually, you're going to reach the point where we get where this criteria becomes critically stable. And that's the critical point. Now, since this is a cubic function, what's happening up here, we have 1 real root plus 2. Right, this equation here will have 1 real root, right? You draw a line, that's the real root. You'll have 2 imaginary roots. Once your temperature falls below your critical point, you will start to get a curved effect here. And in which case, we can delineate regions where we have a stable fluid and regions where we have an unstable fluid. We're going to talk next week, but what ends up happening is that instead of considering this region of stable and unstable fluid, we're going to use a little trick, and we're basically going to say, you can't be in this region. We're actually just going to jump from here to there. And that's the origin of a phase change being predicted by an equation of state. However, the equation of state also has a little bit of additional insight going back to superheating and subcooling. So if I were boiling water, this is not quite the difference, but let's say, for example, we were boiling it by reducing the pressure or expanding it, not by heating it up. I can pass my equilibrium point. And this equilibrium point here is going to be where the Gibbs of the liquid is equal to the Gibbs of the vapor. And that's going to be the challenge of us calculating that moving forward. But I actually can exceed that position for quite some time. But as soon as I hit this point here where the fluid becomes unstable, then it should violently jump over to the equilibrium condition. And that's kind of the origins of superheating and subcooling. Now, cubic equations of state are not necessarily capturing all the physics of the process. But what they are doing is they are capturing enough of the physics of the process to allow us to build a scheme that we can manipulate the mathematics following the first and second law and the stability criteria in order for us to calculate how phase transitions occur. So what's done in a cubic equation of state is that the A, B, C, and D terms have some theoretical basis of foundation. In the case of the van der Waals equation, B corresponds to the excluded volume, A corresponds to the interaction between the molecules. It is formulated and constructed in such a way that it obeys all of the stability criteria of thermodynamics, but in many ways you should view this as strictly a semi-empirical methodology. It's not really capturing all the physics of the process. And that's why we need more advanced equations of state like statistical associating fluid theory, molecular thermodynamics, molecular dynamics, right? Monte Carlo simulations. Those actually incorporate the shape of the molecule, the rigidity of the molecule, how big the molecule is, how easily it rotates, how it hydrogen bonds. In a cubic equation of state, the best you can do is just fudge these parameters until it gives you a good enough fit. So these parameters are modeled to predict this point right here. So if you can predict the critical point with your parameters, then you assume that all the fluids behave the same. So every fluid that obeys the Peng-Robinson fluid is identical. Water, benzene, hexane, they're all identical. The only difference between those fluids is where is the critical pressure, where is the critical density, and where is the critical temperature. But relative to the critical point, every van der Waals fluid is identical. Every Peng-Robinson fluid is identical. Every SRK fluid is identical. Every cubic equation of state fluid is identical. The only difference is where is the critical point. Now for fluids that have weak intermolecular interactions, these can be optimized and tuned quite accurately. For systems that have strong intermolecular interactions, they're not quite so accurate. Where everything absolutely breaks down is in the prediction of liquid properties, right? So what all these equations of state are really good at is they're very good at predicting the phase equilibrium where it will occur from the vapor side. But as soon as you jump over into the liquid side, the predictions become increasingly less accurate. And that's why there's much more advanced thermodynamic theories corresponding to liquid phase equilibrium than there is vapor-liquid equilibrium. So vapor-liquid equilibrium, not too big of a deal. You know, oil and gas industry kind of hammered that out in the 70s because they made a lot of money by figuring out vapor-liquid equilibrium. But when it comes to liquid-liquid properties, there's still much that's unknown. It's extremely difficult to predict liquid density, believe it or not. It's so easy for us to measure it, but to be able to predict density is probably one of the most complicated things you can try and accomplish, especially for a liquid. Because there's so many more considerations than just ABCD coefficients. Molecules don't care about ABCD. Right? Molecules have attractive repulsive interactions, permanent dipoles, oscillating dipoles. Some are rigid, some are flexible. Those all basically correspond to how they move around. Right? So I always think of like molecules as video game characters, and they have set of rules. And they all play differently. And we don't get to control, it's the collective action. So what we'll be moving on to now is applying these equations of state to predict phase equilibrium. Once we handle that for single phase systems, we're going to jump onto multi-phase systems, which will take the majority of the class. We'll touch a little bit about reactions, and then we'll move on to StatMech. So that's kind of the roadmap of where we're going to be moving on in the future. Check your emails. You will be getting an assignment. Sorry to disappoint your holiday weekend, but I hope you all are doing something fun, and I will see you on Wednesday.